In this lesson, we're going to talk about the second law of thermodynamics. So what is the second law of thermodynamics? Well, first of all, remember that the first law of thermodynamics says that matter cannot be created or destroyed, it only changes form. The second law of thermodynamics deals with entropy, and it states the total entropy of a closed system can never decrease over time. It must increase or stay the same. So what is entropy? Well, entropy is a measure of disorderliness. A higher entropy means we have more disorderliness. So think about your house. On its own, it doesn't get any cleaner. If you leave your house for 2 months and come back, the floors aren't going to be shinier than when you left. The furniture is not going to get less dusty. It's going to get dirtier. There's going to be more dust. Things are going to collect. Things are going to tend towards a disorderliness. In fact, it's possible that over time the wood would rot away and the house might even collapse. So that would probably take more than a few weeks or a few months, but nonetheless you get the idea. Houses don't build themselves. They tend to fall down over time. So getting cleaner or more orderly requires energy that's directed to that purpose. So in other words, it can't get cleaner or more orderly than the energy being put into that purpose would allow. So one thing to note though is that adding energy usually makes a system more disorderly. There's actually a lot of special considerations in order for energy to be used to make a system more orderly. But for our purposes, it's most important to note that entropy just naturally increases over time. So the arrow of time. Physics itself, the laws are actually reversible. The exception to this is the law of entropy. And so we can use entropy to establish the direction of time. So what I want you to do is imagine that you're watching a video of a vase breaking. Okay? Imagine you're watching this video. Now let's play that video in reverse. And let's imagine that instead of the vase breaking, the vase is coming back together to form the vase. Well, interestingly, from the perspective of physics, those two ideas are basically equivalent. If we measured the mass and velocity of each of those little pieces that were coming back together, we'd find that they'd actually wind up in basically the same place. So the actual forward and reverse processes are actually the same from the perspective of physics, with one exception, and that's entropy. So we can actually use entropy to establish a direction of time. So the second law is often used in chemistry, and then specifically we use it to analyze chemical reactions. So we can use the second law to figure out which way a chemical reaction will run and at what temperatures it will run. And since everything tends toward more total entropy, the configuration with the most total entropy at the end will tend to be favored. So if we know that, now we need to know how do we measure the entropy so that we know which direction is favored. Well, entropy is denoted as S, capital S, in chemistry. So at our level, absolute entropy is difficult to quantify, so we'll basically look it up in tables. But generally what we work with is the change in entropy, which is delta S. So just like we had the change in enthalpy in the previous section, here we're doing a change in entropy, which is delta S. And in fact, we can restate the second law of thermodynamics in terms of delta S. We can say the delta S of a closed system should always be greater than or equal to 0. So since delta S is the change in entropy, and entropy always increases, then we can say the delta S of a system always increases. So before we get into the mathematics of this, let's talk about some qualitative ideas about chemical reactions in the second law. So entropy is related to the phase of matter. So gas has the highest entropy, liquid has a medium amount of entropy, and solids have the lowest amount of entropy. So generally, all other things being equal, chemical reactions will tend to favor reactions that have gas at the end because that has the highest amount of entropy. So entropy increases with temperature. Entropy increases with more free molecules. So if the end of your reaction has more free molecules, that will tend to be favored by entropy. Entropy increases with more total matter. And then to determine which side of a reaction has the highest entropy, you can kind of perform the following steps to get a good idea about which one. I mean, these aren't exact, but just kind of as a qualitative way of, without looking anything up or doing calculations, we can get a good idea for which side of a chemical reaction has the highest entropy by looking at the following rules. First of all, we're going to look for the side of the equation with the largest number of gas molecules. That will probably have the highest entropy. But what if they're the same or neither one has gas molecules? Well, if the number of gas molecules are equal on both sides, the side with the highest number of liquid molecules will probably have the highest entropy. And if they're still equal, the side with the highest number of total molecules will probably have the highest entropy. And if they're still equal, well, you're stuck having to determine the entropy quantitatively. Okay, so anyway, those are just some general guidelines. I generally favor just calculating it, but nonetheless, that will give you an idea of what entropy is favoring. So let's talk about calculating entropy. So first of all, we have absolute entropy, and that is, so when we had enthalpy, we never really calculated an absolute, or even saw an absolute enthalpy. But with entropy, we do have an absolute entropy. And at standard conditions, this is known as S naught. That little 0 degree sign is called a knot. And anyway, if you see that little circle, what that means is that somebody has found a standardized temperature and other conditions that they're going to make a whole lot of measurements at. So anyway, so we've measured entropy at this certain temperature and set of conditions, and so for a lot of different substances, and those are calculated as they're listed as S naught. So the change in entropy in a reaction can be found by calculating the difference between absolute entropy between the products and reactants. So when we're dealing with standard conditions, the formula for entropy change is simply the delta S of the reaction is equal to the sum of the absolute entropies of the products minus the sum of the absolute entropies of the reactants. This yields an entropy that is in the units joules over moles times degrees Kelvin. The mole will generally get canceled out when we use them in equations. So let me just give you some sample absolute entropies. So you can see on the left is the chemical and on the right is the absolute entropy. And notice that the gases tend to be high 100s or higher. The liquids tend to be a little lower than that. I don't think I have a solid in there, but the solids are still lower in entropy. So anyway, that can kind of give you a taste for what entropies are. And remember, these are joules, not kilojoules. So let's do an example of calculating delta S. Okay, so here is the reaction we're going to look at. 2 water molecules plus an oxygen molecule goes to 2 hydrogen peroxide molecules. So the delta S of this reaction is going to be the sum of the absolute entropies of the products minus the sum of the absolute entropies of the reactants. And we'll simply use the formulas on the previous page to figure this out. So the products is hydrogen peroxide, and its absolute entropy was 110 joules. And there's 2 moles of that. And so 2 times 110 minus 2 times 189, which is the absolute entropy of water, plus 205, which is the absolute entropy of oxygen. And that's going to give us negative 363 joules per degree Kelvin. So since delta S is less than 0, this reaction is not favored. Okay, because remember, delta S, we're generally looking for things where the delta S is greater than 0, where we're getting more entropy. Now, that's not the whole story, though. Delta S does not tell us everything. We also have the concept of Gibbs free energy. Okay, so entropy is only half the story, or I should say entropy of the reaction is only half the story. So the environment is the other half of the story. So a reaction can release energy into its environment. That's what we looked at with enthalpy. And when it does that, it increases the entropy of the environment. Okay, and so that's another way that entropy of the system is increased overall. So Gibbs free energy combines the concept of entropy of the chemicals in the reaction themselves, that was delta S, with the effect of that the enthalpy change, the delta H, will have on the environment. So basically how Gibbs free energy works is that as the temperature increases, the importance of entropy compared to enthalpy increases. So this is reflected in the equation for Gibbs free energy, which is delta G, which is Gibbs free energy, is equal to delta H, which is our change in enthalpy, minus our temperature, and that's absolute temperature in degrees Kelvin, times our delta S, our change in entropy. So just remember that delta S is normally in joules, but delta H is normally in kilojoules. So we have to multiply our delta H by 1,000 to get them both into the same units. So note that delta H and delta S don't generally change much with temperature. They do change a little bit, but not a lot. So we can actually approximate them by whatever the values that we have that were based on standard conditions. So delta H will be equal to delta H naught, and delta S will be basically equal to delta S naught. So you don't have to worry, even though that these enthalpies and entropies were calculated at a particular set of temperature and pressure. They really don't change a whole lot when you vary the temperature. So if our Gibbs free energy is greater than 0, then the reaction cannot move forward because it violates the second law of thermodynamics. So here's an example. Does the Gibbs free energy favor the reaction that we were looking at earlier at 298 Kelvin? So we'll have 2H2O plus oxygen goes to 2 hydrogen peroxide. So earlier we determined that the entropy for this was negative 363 joules per degree Kelvin, and so it was not favored by entropy. Is it possibly favored overall by Gibbs free energy? Well, the enthalpy of this reaction is 198,000 joules. So the Gibbs free energy is our delta H, which is our 198,000 joules, and that's a positive 198,000 joules, minus the temperature at Kelvin times the entropy, and that yields a number that is our Gibbs free energy. And since our Gibbs free energy is positive, this reaction would violate the second law of thermodynamics, so it would not be possible. So for this next example, we're going to use Gibbs free energy in a slightly different way. So some reactions occur only at certain temperatures. And we can find the cutover point for when this is favored and not favored by looking for the temperature when our Gibbs free energy is 0. Because if you think about it, if it's varying, if the Gibbs free energy is varying based on temperature, well, we find out where it's 0, and that's going to tell us where the cutover point is between it being favored and not favored. So here's the reaction we're going to look at. So it's nitrogen plus hydrogen goes to ammonia. Okay, And so this has a delta S of negative 199 joules per Kelvin. So it is not favored by entropy. And it has a delta H of negative 92.2 kilojoules. Okay, so that means it is favored by enthalpy. So Gibbs free energy is given by delta T equals delta H minus temperature times delta S. So our delta H is negative 92,200. Remember, we have to multiply that our change in enthalpy by 1,000 because it's in kilojoules, minus T times negative 199 because our temperature is unknown. So that, and if we've got two negative signs there, so it becomes negative 92,200 plus 199 T. So now, if we want to find the cutover point, we set delta G to 0. And so 0 equals 92,200 plus 199T. 199T equals 92,200, and T is approximately 463. So what that means is that 463 is the cutover point, but is it favored above or below that temperature? Well, if we look at the equation, we can see that delta G, our Gibbs free energy, increases with temperature, and Gibbs free energy increasing is unfavorable. So therefore it only occurs below that temperature. So a few notes to point out. So start out with our Gibbs free energy equation. So if the reaction is exothermic, where delta H is negative, but it loses entropy, so that means that delta S is negative, then lowering the temperature makes the reaction more thermodynamically favorable. On the other hand, if the reaction is endothermic, which means delta H is positive, but gains entropy, which means delta S is positive, then raising the temperature makes the reaction more thermodynamically favorable. Okay? So if the reaction is unfavorable in both directions, then usually the chemist must involve more chemicals to make the reaction work. So the final state of the system will be thermodynamically favorable. So usually it means he's got to come up with a more complex reaction or set of reactions so that the end products, he's got to include more things so that the end products will have will be more thermodynamically favorable. So we talked about state functions last time, and Gibbs free energy is also a state function. So for a given temperature, we can compute the Gibbs free energy of reaction by using tables that have Gibbs free energy of formation for both the products and the reactants. And the way we do this is just like before, just like we did with enthalpy. And if we have the Gibbs free energy of formation of the products and the Gibbs free energy of formation of the reactants, we just add those up and subtract them, and that will give us our Gibbs free energy of the reaction. This is a little less useful though, because the whole point of Gibbs free energy is to allow us to adjust for temperature, and that will tell us about the balance between enthalpy and entropy. So doing this is less useful than the other calculation. All right, so that's Gibbs free energy. So then we also have not everything that's thermodynamically favorable will actually happen. There's a lot of other factors that go into this, and one of them is activation energy. So just because a reaction is possible with thermodynamics does not mean that it will definitely happen. And one requirement is activation energy. And activation energy is the amount of energy required for a reaction to get started. So after the activation energy is applied, then the reaction can move forward, and the amount of activation energy is essentially given back to the system. So let's take a look at a graph to see what this looks like. So if we have this graph, you can see this is basically the y-axis is the amount of energy, and the x-axis is over time. So you see the starting energy starts out, and then you get a bump of energy, and that kicks off the reaction. The reaction will give off energy, and it will finally settle off to a point after the reaction. So delta H is the difference between the beginning state and the ending state. Delta H does not worry about activation energy. And the example to think about is that if, let's say that we're combusting something, usually you need a spark to initiate the combustion. So your spark is your activation energy. After the activation energy, then the reaction proceeds as normally, but the spark is required to get it started. And so that brings us to another topic, which is catalysts. And a catalyst is a substance that makes a reaction more likely, but is not consumed by the reaction. And catalysts often work by altering the activation energies for one or more reactions or steps in a reaction in order to favor one or another. And they often work by altering the reaction pathway, like which order of things the actual reaction does. But in any case, what the catalyst generally does, the general method is by reducing the amount of activation energy to perform some particular chemical reaction. So, in summary, entropy is the amount of disorder that exists in a system. The second law of thermodynamics requires that the entropy of the whole system never decreases. The entropy of a reaction is given by delta S, and it's favorable if delta S is greater than 0. But in addition to its own entropy, a reaction can affect the entropy of its environment through its delta H. And whether or not the reaction is allowed by the second law of thermodynamics is based on a combination of these considerations. And this is expressed with Gibbs free energy, which has the equation delta G equals our change in enthalpy minus the temperature times the change in entropy. If Gibbs free energy is less than 0, the reaction is thermodynamically possible. Now, being possible is not the same thing as actually occurring, as there are other considerations as to whether or not a reaction will actually occur. For example, how much activation energy it requires.